Hello, my name is Hossein Pishronik and I am presenting a joint work with my PhD student Saideh Nayati. Our goal here is to provide a framework for probabilistic decision making using change of probability measures. Probabilistic decision making is a fundamental problem. It has been studied in many different disciplines such as engineering, computer science, philosophy, economics, and other social sciences. In a typical scenario, you have an agent which could be a human or an AI agent, and the agent is faced with m potential options, and given the option that the agent chooses, some reward or some utility is obtained. For example, if the agent chooses option 1, the reward is shown by the random variable x1, and so on with x2, x3, up to xm for m potential options. The assumption here is that we know the distribution of these random variables. So the question is, which one is the best? Which option should the agent choose? While this problem of decision making has been studied for many years in different disciplines, its importance is further increasing because of the rise of AI and AI decision making. If you think about it, the outcome of any machine learning algorithm can be interpreted as probabilities. For example, if you have a classification problem, the output gives you the probability of each class. So essentially, the probabilities are given to you, and based on these, you make a decision. Another trend is that more and more high-impact decisions are going to be made by AI in near future. For example, in the areas of medicine, economy, defense, security, and so on. So all of these imply that it is more important to have a systematic and rigorous framework for probabilistic decision making. Now, when you are thinking about decision making, decision theory provides some good answers. In particular, if you look at the expected utility theory, you can use it to successfully address many decision making problems. The basic idea here is that you choose the option with the highest expected value or highest expected utility. Now, while very powerful for many problems, expected utility also has many limitations. A very key and important limitation that you would like to focus here is that the expected utility theory implicitly assumes that the decisions that you are making are in environments where the laws of large numbers hold in some sense. If you think about it, the very notion of probability and expected utility are asymptotic. Probabilities and expected values are what we observe in the long run. So, if you have a scenario that you are making a lot of decisions and each decision by itself does not dominate the whole thing and has a kind of a small impact on the total, then the law of large numbers hold and expected utility works perfectly and beautifully. But what if the agent is making a high impact decision that is not repeatable or repeatable only a few times? What it means is that you cannot use the law of large numbers anymore. So in this context, it is not clear how to make your decisions, and the problem of decision making becomes much more complicated. So that's why we want to focus on this kind of context. We would like to make progress to providing a non-asymptotic framework for probabilistic decision making. We would like to have a framework that can be applied to both non-LLN and LLN regimes. So we can apply it to the scenarios where the law of large numbers hold, but more importantly, we should be able to apply it to the scenarios that the law of large numbers does not hold. Our framework is based on change of probability measures, and as you will see, it can be considered as a generalization for the expected utility theory from several perspectives. To get a better insight, let's look at a few problems. We start with the St. Petersburg paradox. It is a well-known problem, and the question is the following. A fair coin is tossed until a head is observed for the first time. Let k be the number of resulting coin tosses, so it is a geometric random variable. And let's say you are facing this gamble that your utility is going to be equal to 2 to the power of k. So you will receive 2 to the k units of utility, where k is the total number of coin tosses in this problem. Now, the question is, how much is this gamble worth? Based on expected utility theory, if you compute the expected value, it becomes infinity. Now, it doesn't seem to be reasonable to pay a huge sum of money for such a game. So the question becomes, how much should you pay for this game? Now, in general, if you think about this, in terms of financial decision making, any time that you are making a decision in which the amount of financial transactions could be huge and can have big financial consequences, then you are facing a high impact decision in this regard. And that's where the law of large numbers does not hold anymore, and you have to have a more sophisticated approach than expected utility. Now let's look at another example. In this example, a plaintiff is in a court dilemma with two options. In option 1, she can accept a settlement where she receives $1 million. Let's assume that she assigns 10 units of utility to $1 million. Now, she can also reject the settlement and go to the court. In that case, she will win the case with probability 35% and will win $10 million. Let's say she assigns 40 units of utility to this reward. She also might lose the case with probability 65%. And in that case, she does not win anything, and because of the regret and disappointment, she assigns minus 5 units of utility to this outcome. So the question is, which option is the best? I think most people agree that option 1 is better. In option 2, with probability 65%, you are facing the worst possible outcome. However, if you just maximize expected utility, it turns out that option 2 has a higher expected utility. So again, this is a scenario where the amount of money is significant, and from the financial perspective, this is a high impact decision. And again, it might not be reasonable to use just expected utility. Of course, if the person is extremely wealthy, it could be a different story. If the person is making transactions in the order of millions of dollars every day, in that context, this is not a high impact decision anymore. And she can go with the expected utility principle because over the long term, she's the winner of the whole situation. So we are focusing on scenarios where, depending on the context, we know that the decision is a high impact decision, and we cannot just simply treat it as another decision that can be combined and absorbed to many other similar decisions. To get a better insight, let's go back to the St. Petersburg problem and change the problem a little bit. Let's assume that the agent can repeat the game n times, and for each play, the agent pays a constant amount of C dollars. So in total, the agent pays n times C dollars. So if you look at it in this way, something interesting happens. In fact, if you show the average reward by X bar, then you can show that the probability that X bar is greater than C goes to 1 as n goes to infinity. What does this mean? It means that if the person is able to repeat the game many times, then even if she pays a lot of money for that game, eventually she is the winner. So depending on how many times you are allowed to repeat the decision, the value of the game changes. And this gives us a key idea. Our framework must be able to cover such aspects of decision making. To summarize, we have scenarios in which we have a decision-making problem that cannot be aggregated into a large set of similar decisions. What it means is that the laws of large numbers do not work here. A very important example is when you are making a high-impact decision and the outcome might have big consequences. So expected utility is not sufficient anymore, and we need to have a more comprehensive way of decision-making, and that is our goal here. In this work, we provide a general framework based on change of probability measures, and as you will see, it can be considered as a generalization of the expected utility theory from two different perspectives. First, it can handle the number of repetitions. As the number of repetitions grows, the answer that is obtained by our proposed method approaches to the expected utility decision. So, if you are able to repeat the decision a large number of times, then you are back to the expected utility. Also, there is an important parameter, epsilon, in our framework. If you set the epsilon to 0, you are back to the expected utility, but in general, you get a different answer. Using this framework, we are able to provide insights to some real-life situations. For example, when we apply it to right-tailed distributions, we obtain some insights to the dynamics behind the venture capital industry. And when we apply it to left-tailed distributions, we obtain some insights regarding robustness and fragility of decision policies. And finally, it turns out that we can get satisfactory results for the two problems that I mentioned in this video. So the proposed framework has some potential to guide us in decision-making problems where the laws of large numbers do not hold. Instead of going to the general setting, I would like to provide a very simple special case of our proposed method to get insights. So let's consider what we call bounded expectation. It is a metric for evaluating random rewards. It is based on the accepted principle of rationally negligible probabilities that says that if something has an extremely low probability, we can ignore it in decision making. We actually use this principle in our everyday decision making. The problem is that we don't have a systematic way of applying it. Bounded expectation is a way to do that. The idea is very simple. Imagine you take a large IID sample from your distribution. So you observe a large number of outcomes. If you look at the tails of the distribution, there are some outliers, some values that are extremely large or extremely small, but their aggregate probability is sufficiently small. Let's say the total probability is less than 10 to the power of minus 3 or 10 to the power of minus 4. These probabilities are really small and we can ignore them. So instead of taking the expected value, we take the conditional expectation given that x is in the normal set. In other words, we are removing extremely unlikely values from both tails of the distribution, and then we take the conditional expected value. This is the intuition behind bounded expectation. Let's apply bounded expectation to the St. Petersburg problem. So instead of computing normal expected value, we compute the conditional expectation given that x belongs to the normal set. In this case, we can evaluate the per game value by the number of times we are able to repeat the game. Now, as we expect, we see that the value of the game increases as the number of allowed repetition grows. So as the number of repetition increases, you must be ready to pay more and more for each game. In fact, if you are able to repeat the game infinitely many times, the per game value goes to infinity as we expected. Although bounded expectation seems to be a simple measure, it is able to provide a satisfactory answer to the St. Petersburg problem. So if you look at the problem from this perspective, there is no paradox. Depending on how many times you are able to repeat the game, you need to pay more for the game. Bounded expectation has some interesting properties. For example, it is nonlinear. Specifically, the value of x plus y is normally larger than the value of x plus the value of y if you have a right-tailed distribution. So what does it tell us? In fact, it could help us to get some insight to some scenarios such as the venture capital industry. If you think about it, a venture capitalist is able to invest in a large number of startups. Each startup has a very small probability of success, and the reward is right-tailed. So the value of each startup is not very large, but the total portfolio has a bigger value than the summation of each individual item in the portfolio. This graph shows this phenomenon using bounded expectation. As the number of startups in the portfolio increases, the gap between the individual value and the average value increases. This observation is consistent with observations and analyses performed by financial experts and risk analysts about the venture capital industry. Now, the same phenomenon happens in reverse when you look at left-tailed distributions. This case applies to scenarios where you are taking risks. You might be taking a lot of risks. Each risk by itself is acceptable, but when you put them together, the aggregate risk might be larger than what is acceptable. The aggregate risk becomes bigger and bigger than the sum of the individual risks. Again, this is consistent with empirical and analytical studies. In sum, bounded expectation has some useful and desirable properties, but it also has many limitations. In fact, if you apply it to our court problem, the answer is not that much different from what you get from just applying expected utility. So, although bounded expectation has some potentials, it is not yet a satisfactory strategy for decision making because of its shortcomings. Nevertheless, bounded expectation gives us some ideas on how to move toward a more general theory. Let's remember how bounded expectation works. Well, the idea is very simple. You have the distribution and you look at the very left and the right side of the tails and you reduce those probabilities to 0, but you don't do much about the rest of the probability space. All you do is make sure that the probabilities sum to 1. So essentially, you are abruptly changing the probability of tails to 0 and you don't touch the rest of the probability space. So bounded expectation only focuses on a very small part of the probability space and does not have a global view. This could give us an idea to obtain a better approach. You could take a global view and you also can perform smoother operations. The key idea is the following. When we are making a single decision about which the law of large numbers cannot be used, we should weaken the highly improbable outcomes and focus on the most likely outcomes. This is the key idea and can be done essentially by changing the probability measure. You change P to some other probability measure, say Q. This change of measure is done in a way to suit the non-LLN nature of the problem. It weakens the highly unlikely outcomes and focuses more on the most likely outcomes. Essentially, instead of taking the expected value of x, You now are taking the expected value based on a different probability measure Q. This change of measure operation that we propose here is done by taking into account the distributions of all the involved random variables. Now, of course, if you want to do this, you have to be extremely careful because you want to do it in a principled way. You are actually distorting your probability measure, so you have to be careful and do it in a way that important properties are satisfied so that you have a proper way of making your decision. And that is a key part of our work. Essentially, we have provided several important conditions that must be satisfied such that this kind of change of measure is acceptable. So, when all of these properties are satisfied, we call it an epsilon consistent change of probability measure operation. In particular, the parameter epsilon here is very important because it is a measure of distortion. It shows how much you are distorting your probability measure. In other words, if you look at any event, the difference of the probabilities of this event under these two probability measures must be less than or equal to epsilon. So how can we construct such epsilon consistent change of probability measures? In the paper, we provide one specific way of doing it using what we call consistent functions. These are a class of functions that we can easily build and have some nice properties. Here is an example of some of them. To obtain the change of measure operation, we apply the function g to the tail function of the random variables. In this figure, if you take line y equals x, you are back to the expected utility, and so you are not changing your probability measure. Now, if you look at the red dashed line, you are distorting your probability measure a little bit, and you are going from the measure p to the measure q using this g of x. So we have this change of probability measure. How can we use it in decision making? We propose a systematic approach for probabilistic decision making. The idea is the following. You start with epsilon equals 0. In this case, you are back to the traditional expected utility. Now, you gradually increase epsilon, and you see how your preferences are changing. In other words, when epsilon is equal to 0, maybe option 2 is the best option. Now, as you increase epsilon, at some point, the best option changes for the first time. We show the corresponding epsilon by epsilon star. So, what does this epsilon star tell us? Actually, if epsilon star is large, it means that you need to distort your probability measure significantly before the result of expected utility is not valid anymore. In other words, it tells you that the expected utility gives you the best answer. On the other hand, if epsilon star is very small, it tells you that the result of the expected utility is unstable. It is probably preferable to choose the option suggested by epsilon star. So the value of epsilon star gives you the stability of the results obtained by expected utility. Of course, for further research, it is important to get a better insight on the threshold epsilon to decide based on that. But as a rule of thumb, we think for epsilon star less than 5%, there is a strong indication that the results given by expected utility might not be acceptable, and the options suggested by epsilon star might be preferable. In some sense, epsilon star has a similar role as the p-value in statistics. If it is small, then there is a strong indication that the result obtained by expected utility is unstable. As the problem of decision making under non-LLN regimes is a multifaceted problem, and most likely a simple narrow approach will not be enough, the proposed method where you look at how the preferences change as epsilon changes seem to be a step in the right direction. Now let's apply this method to the St. Petersburg problem with a specific g of x given here. As you observe, for a very small value of the epsilon star, the value of the game becomes extremely small, less than $13, which essentially tells us that the answer given by the expected utility is not acceptable. In other words, if you are choosing between getting $13 for sure or the result of the St. Petersburg game, it is reasonable to get the $13. Of course, the value of the game increases as the number of allowed repetitions grows, as we saw before. And the same scenario happens to the court dilemma. Again, at a very small amount of epsilon star, the preferences change, which indicates it is a better idea to choose the settlement rather than going to the court. Now let me provide a brief summary and discussion here. In this work, we argued that the increase of high-impact AI decision-making further amplifies the importance of a rigorous and formal view of decision making under non-LLN regimes. Here, we proposed a framework using the change of probability measures, and we saw that we could get some satisfactory results and insights for some problems. I should emphasize this fact that the problem of decision making under non-LLN regimes is a very complex and multifaceted problem. So most likely, we cannot provide a single framework that answers all problems. Although the proposed framework is providing some reasonable answers to some problems, there are other problems that probably the answer might not be good enough. So because of this, we conclude that there are a lot of promising research directions that can be investigated going forward. For example, we can apply the proposed framework to different high-impact problems in different areas and see how it works. For some problems, the method works well. For some other problems, the method might not work very well, and this helps us to further improve the method. The good news is that the approach is general and has a lot of flexibility. A very promising aspect is that the proposed method can be easily combined with other techniques, because essentially all it says is that you change your probability measure a little bit and then you can do anything you want with it. So it would be very interesting to study how these methods can be combined and hopefully improve the entire strategy of decision making. Now, there are many technical aspects of the problem that can be studied. For example, you might want to add to the required conditions to further restrict your change of probability measures to improve them or make them more powerful. Another direction is using tighter bounds than the union bound that we used in the paper to obtain stronger results. In general, there seem to be a lot of interesting research directions for going forward. Okay, thank you very much.